Very good morning. Last time we have dealt with first order linear differential equations and Bernoulli equation, and we try to identify what will be the possible integrating factor and what will be the shape of the solution, final solution. Okay. Now we want to generalize the result more. Okay, maybe sometimes the equation may not be linear, but still, how we may be able to solve that problem. Okay, right. So let's consider this standard form. Okay, and which can be equivalently written as in the following form. So I don't think so there is any problem for understanding that you can from here to here or here to here, you can always come. Okay, so if you have this, for example, I just give you one or two examples. So let's say dy by dx equals to x into y. So you can write, this implies I can write x into y dx plus minus dy equals to 0. That's the one thing. Or you can also write x times dx minus 1 by y times dy is equals to 0. Okay. Or dx minus dy by x into y equals to 0. So you can always write, able to write this form into this form. That's with one example I have try to explain you. Okay, so there are different ways to write it. Okay, now if the equation takes after taking this shape, then how would you able to solve this problem? So now if you recall, if you have a function of let's say f of x comma y, or f is already we have used the notation. So let me take capital F, and which is a function of two variables. It's not it's like two variables, but function y is a function of x, and x is independent. And then you try to find out total differential of this. Okay, then you try to identify the total differential. So if you apply that rule, total differential with respect to x, okay, or you can have, this is going to be, you can differentiate f with respect to x partially, and then you have dx plus you have, this is dou f by dou y dy. Okay, so if you are able to recall from your intermediate sessions, I think that is very straightforward. Now suppose the right hand side is here is for some function f df of x comma y. So then it is easy to solve if it is possible that you are able to find out such a function f which is such that df is equals to this by some way. Means like whether by, you can say by hook or crook, you can say, simple. Okay, so if it is so, then the solution of this equation, so you have, this is df equals to 0. What will be the solution of this is, so first differential is a one parameter family, which is nothing but f of x comma y is equals to c, the constant. So df equals to total differential of f is 0, means df is equals to, means f is constant. Okay, f is a function of xy, and that is equals to constant. That will give you that parameter family which solves this equation. Means essentially this solves this. Now how, means you can relate the total differential and this differential equation is, so as I already mentioned you, if the left hand side of this spatial form, you can say, or it's not a spatial form, it of this form. Okay, if you are able to write in this way, so you, for some capital F, then this left side expression is called exact differential. Okay, so I have the following definition now. So if there exists f of x comma y such that this is m of x comma y dx plus n of x comma y dy is equals to df. So certainly we are talking about in a domain D or in xy plane where all these things are possible. So I hope that is a follow up here, that when you are talking about a total differential, okay. So if you look at this definition, total differential involve these things, okay, dou f by dou x, dou f by dou y. So all these things means the function is so nice that these are possible things. Okay, means this partial derivative you can say exists, and moreover you can also later on you will see we require the continuity as well for the partial derivatives. Okay, so far means like we are only restricted with the one variable case. Okay, so I'm not going much detail into it. Okay, so but for the total differential, when you're writing this form, so left hand side and right hand side will both have meaning only when this dou f by dou x and dou f by dou y exist. Okay, exist, and if they are continuous, we can talk about that is maybe later. So where it is continuous or exists means in some certain domain D. So okay. So if this you have there exists some capital F such that this happens, then that this is it. Then we say that they say that this m dx plus n dy is exact differential. Okay, exact differential. And then you have, this is, I can say, and if I can write here straightforward, if m dx plus n dy is exact differential, so ed I'm writing as a short form, then this then m dx plus n dy equals to 0 is called exact differential equation. Okay, so if the left hand side expression you can write as a total differential for some function f of x comma y, okay, then this equation is called an exact differential equation. Now suppose everything is nice, it's like suppose this is an exact differential equation, let's say, okay, but how we are going to solve this problem now? So how do you identify this capital F? Okay, so let there exist capital F sorry, F such that df is equals to f dx plus n dy. See, here onwards I am using these annotations, like instead of m of x comma y, n of x comma y, means it is understood that here after that they are x and y, so I am using some, you can say, abuse notation hereafter. Okay, right. So let's say there exists f such that this, so this happens when this is if and only if, since dx and dy are the small element along x-axis and y-axis independent, so certainly you can show that this is if and only if m is equals to dou f by dou x and n equals to dou f by dou y. Okay, so this capital F can be obtained by solving these two equations. Okay, so if they let there exist this, then this is happen. So if and only if this happens, if and only if m is equals to dou f by dou x and n equals to dou f by dou y, if this is a total differential. If it is not, you will, I mean, if you start with this equation, you will get some absurd things. So, or you will not be able to solve the problem. Okay, right. So let's take one problem and we will move further then. Okay, I will take one problem. Okay, so I will take this problem here. So y square dx plus, so I'm just taking one problem. Let's say y square dx plus 2xy dy is equals to 0. So now you comparing with, I'm just writing once upon a time m dx plus n dy equals to 0. We get m is equals to dx coefficient, that is y square, n is equals to 2xy. Okay, so I'm starting with the assumption that, okay, assumption here, I'm starting with an assumption. You will say it may be fail or it may be not fail. We will see assumption that there exists capital F such that capital M is equals to dou F by dou X and capital N by dou F by dou Y. Okay, so now so dou F by dou X is equals to M, and what is M is y square, and dou F by dou Y is equals to 2xy. So I hope this type of equations you must have solved in somewhere when you are talking about some gradient. Okay, but else means like somewhere you have solved such type of problems. So what I do? So now let's start with the first equation. Let's say dou F by dou X equals to y square. What I will do with this? So I will integrate. So see, left hand side is a partial derivative with respect to x. So you will perform the partial integration with respect to x. Okay. So when you are integrating partially with respect to x, in that case, x and y are independent random variable. We have to treat them as a independent variable. Means, okay, means when you are integrating partially with respect to x, y square will be treated as a constant. Means I'm talking about only partial integration. I'm not talking about the derivative, find the total derivative. That okay. So integrating both sides partially with respect to x. Okay. So what we will get is f of x comma y. So integration is partially with respect to x is nothing but f only, f of x comma y is equals to, what about right side, is x times y square plus some constant. But now, as I already mentioned you, that y square you have to treat as a constant only. So it may or may not be a function of y, but we have to keep it. So when you perform the dou F by dou X here, you will only remaining with y square. So these are equivalent. Okay, because the dou F by dou phi by dou X, the partial derivative of this function with respect to x, which is purely the function of y, is 0. Okay, right. So now this is the time I can use now the second equation. What is the second equation? Is you have second equation is dou F by dou Y is equals to 2xy. That is there. Okay, so now let's differentiate partially with respect to y. Okay, so this implies dou F by dou Y is equals to, so what about the partial derivative with respect to y? So x is treated as a constant when you are differentiating partially with respect to y, not the total. I'm not talking about total. So that's going to be 2xy plus t dash of y. Since it's a single variable function, so whenever you are talking about the d phi by dy or dou phi by dou y, both are the same thing. Okay, right. Now, since dou f by dou y is equals to 2xy. This implies phi dash of y is equals to 0.
Sir,
Right? Because dou f by dou y is 2xy. So you will get cancelled, 2xy will get cancelled, you will remain with the phi dash y is 0. So this implies, so this is a d phi by d phi by dy. Okay, so you can use variable separable method, or you can say surely that phi of y is a constant. Even it is not depend on y itself. So what will be the final family is as follows. So this implies f of x comma y is equals to x into y square plus c. Okay, so that's a family of solution for the original equation. And all these stuff are possible because you have reached up to this level, because this equation is means like you can say exact only. We have not verified that whether it is exact or not, but we have started with an assumption. Okay, right. So if somebody
sir,
has question, yeah.
yes, sir. In the last slide, when we did dou f by dou y, why it is means 2xy? Shouldn't y be integrated and written as y square by 2?
Why we integrated where? See, we are differentiating now. We are not integrating. That's very first thing. Partially with respect to y. Okay, so partially with respect to y means what? You are differentiating. So x is like a time y square. So what is the derivative of y square? Is 2y. So in total, what is the partial derivative is 2xy.
Okay, okay.
Okay,
Sir,
right. Yeah.
so in the yes, the in the first time you write out d f by dy is equal to 2xy, and then you write 2xy plus pi dash y. So I can't understand that.
No, no, no. This dou f by dou y is coming from here. Okay, now
Yes.
since we have already in hand that dou f by dou y, see, when you are making the assumption that there exists this such that this and this happens, so it says that dou f by dou y must be equals to 2xy if this assumption is true,
Okay,
and
sir.
dou f
Yes,
by
I
dou
got
x
it.
is y square.
Yes, okay, sir. Okay.
Okay, right. Okay, so similarly, I can hope that second example we can solve easily. So what is happening here is, now let me also figure out this. So when you have this m dx plus n dy equals to 0 is exact differential equation, means implies there exists capital F such that df is equals to m dx plus n dy. So we certainly require a criteria before starting with this all this stuff. Okay, so this is if and only if you have, this is capital M is equals to dou f by dou x, and capital N is equals to dou f by dou y. Okay, now see, when you differentiate, see, I want to have a equivalent criteria. Okay, so this is true. I'm writing here if and only if something will happen. Okay, so dou m by dou y is equals to dou square f by dou y dou x, and dou m by dou x is equals to dou square f by dou x dou y. So now you can see the right side in each part, it's same as like dou square f by dou y dou x, dou square f by dou x dou y. Means first you are differentiating partially with respect to x, then with respect to y, or first with respect to y and then with respect to x. So then I will means like, since again I'm having this I can't go beyond the scope of this course. What I can say is here the mixed derivative theorem. So there is a mixed derivative theorem that you can, if you are interested, you can search on Google as well. Okay, so mixed derivative theorem tells you that if you have first order and second order partial derivatives continuous, okay, then whether you differentiate first x partially with respect to x and then with respect to y, or first with respect to y or then with respect to x, both are will give you the same answer. Okay, so what it tells you is, so I'm just going to use that here. So assume that this is if and only if you have, this is dou m by dou y is equals to dou n by dou x. Okay, so means whenever, means like you have m and n has continuous first partial derivatives. Continuous first partial derivative, so means that those can f by that also continuous, and c. So this will be the criteria which you need to check, okay, to verify that whether the given differential equation is exact or not. Okay, so now if I look back at that example, I will check. So that was y square dx plus 2xy dy equals to 0. Okay, so if I compare, have that m is equals to y square, n is equals to 2xy. Not that the dx coefficient is m, dy coefficient is n. If you change the role of m and n, the situation will change. So if you make dy coefficient as m and dx coefficient as n, then you have dou n by dou y is equals to dou m by dou x. Okay, so don't change the rule. Be aware with this notation. Okay, right. Now, so dx coefficient is partial differentiation with respect to y, and dy coefficient partial differential with respect to x. Dy coefficient with respect to x, dx coefficient with respect to y. So if you look at what is the derivative, partial derivative with respect to y is 2y, and what is dou n by dou x is here is equals to also 2y. Okay, partial derivative with respect to x, so 2y is a constant for that case when you differentiate it partially. So this implies dou m by dou y is equals to dou n by dou x. So you can certainly say that this implies you have this is, let's say, 1. So 1 is exact differential equation. Okay, so 1 is an exact differential equation, and then you can now start with that assumption. What we have started just with like this assumption. So this gives you guarantee that there certainly exists such f, that which we are searching for, like capital M is equals to dou f by dou x and a capital N by dou f by dou y. Okay, so the procedure will remain same for solving the problem. Okay, so if the equation is exact, now the case when suppose equation is non-exact means what? You already learned. So if I say the equation is non-exact means you have that equality is not there. Okay, so I will say this is again say this is equation m dx plus n dy equals to 0 is a non-exact differential equation if dou f by dou y is not equals to dou n by dou x. So verify this condition, that dou f by dou y whether equals to dou n by dou x or not. So if it is equal, you can say that that's the differential equation. If it is not equal, you will say that that is non-exact differential equation. Okay, now we just now see that how do we handle the exact differential case. Now we want to see how would we handle the non-exact differential equation. Okay, right. So now, like in the case linear first order differential equation, we multiplied the equation by some function mu of mu there, and then we have driven some derivation there and get that integrating factor. Okay, so similarly we are going to do this here as well. Okay, so now let's say, now let m dx plus n dy, okay, is such that this is dou m by dou y is not equals to dou m by dou x. Means it automatically says that it's non-exact differential equation. Now let let that mu, again I'm using that same notation, mu function of xy be such that this m time mu dx plus n time mu dy is equals to 0, okay, becomes exact. Okay, so let mu be such that this happens. So means, like, suppose you are multiplying both sides by this mu, afterwards you are getting that, means the left hand side becomes an exact differential, then means becomes exact, and then you can start solving the equation. So such mu is called integrating factor of 1. So I can or of star, let's say star. So let's give this number as star. Let's give this number. Okay, now once we have stated that after multiplying by mu this becomes exact, means what? Okay, so this exact means what? Let's derive this for a little further. Okay, so now since m time mu dx plus n time mu dy is equals to 0 is exact differential equation. So this implies, this is if and only if, or you can say implies, dou by dou y, partial derivative of dx coefficient is same as the partial derivative with respect to x of dy coefficient. I'm applying just the condition. Now it means you have got the modified m now and modified n now, because after multiplying you will get a new dx coefficient and dy coefficient. So this implies, so both m and mu, n and mu, all three functions, all these three are function of x and y. Okay, then you are differentiating partially with respect to y. So this is if you apply the product rule, what you will have is mu time dou m by dou y plus mu plus m time dou mu by dou y is equals to dou n by dou x mu time plus n time dou mu by dou x. Now this implies, so mu is common here, so I will just write down now m time dou mu by dou y minus n time dou mu by dou x is equals to mu time dou n by dou x minus dou m by dou y. I just rearrange the things on the left side and right hand side. I think that is very easy to verify. Now, so this is here now. Okay, I think everything is simplified. Now what we can do is we can further make assumption. Okay, so I'm just assuming now what I'm assuming. Let mu of x comma y, okay, let's say, means you can say case 1 is a function of x only, function of x only. Let's say be a function of x only. Okay, then what will happen in that case? So if it's a function of x only, so this implies function of x only means what? It's not a function of y. Y is not explicitly there, so it implies dou mu by dou y is 0. Okay, and I will say this equation as, let's say, double star. So when dou mu by dou y is 0, so this term will not be happening in the double star. What will happen remaining with this term and the right side? Okay, so then what double star gives you implies it implies the following. Just writing this is going to be minus n dou mu by dou x is equals to mu time dou m by dou x minus dou m by dou y. Now, since mu is a function of x only, so I can replace dou mu by dou x by d mu by dx, because partial derivative or total derivative in that case same. Okay, that's a very okay. So this implies, and I can send this minus on this side. Okay, so what I am saying here, so this implies d mu by dx 1 by mu is equals to dou m by dou y minus dou n by dou x divided by n. Okay, so I have rearranged the things, and now I have taken the following simplified form now. Now, what it tells you, this identity only possible when, what, see, left hand side is purely a function of x only, because mu is a function of x, so d mu by dx also a function of x. 1 by mu is also a function of x. So this totally left hand side is a function of x. So these two identity are only possible whenever this is a function of x. Okay, and so this will be, let's say, this function is going to be purely a function of x only. This is true. Okay, it has to be. It will come automatically. That is going to be a function of x only. So when this happens, so what will be the solution for this case? That you have already known. So let's say this is this implies you have this is d mu by dx minus g of x times mu is equals to 0. And you know what will be the solution for this first order linear differential equation is mu is equals to e to the power integration of g of x dx plus some arbitrary constant. So we are not taking care of arbitrary constants here, because it anyway it's going to be turned out into the final solution. So we are not taking care of arbitrary constant in this here when we are writing the integrating factor. So what is gx is where g of x is nothing but dou m by dou y minus dou n by dou x divided by n. So what it suggests you? It suggests you the following now. Now I'm concluding. So I'm concluding now. From this case, for this case, what you can have here is you have if dou m by dou y minus dou n by dou x divided by n is a function of x only. Function of x only. So this derives the following. Then let's say this is then mu is equals to that integrating factor. Okay, then this integrating factor is equals to also a function of x, and that is going to give you e to the power integration of g of x dx, where g of x is equals to dou m by dou y minus dou n by dou x divided by n. So this concludes the following. Okay, right. So whenever this equation is not exact, so you have to check this condition. Means this is the meaning. So this ratio You have to check whether it comes out as a function of x only. Then integrating factor is simple to write. Integrating factor is mu is equals to this. So once you have this integrating factor, you multiply the equation by this mu, and you can verify that resulting equation becomes the exact differential equation. Okay, and whose solution you can find in the same way what we have done for the exact differential. Okay, right. Now let's discuss the case 2. Okay, so case 2, this at you can
Sir,
this is one of the method you can say to identify the integrating factor for certain differential equations. So let's say method 1 or type 1. Yeah,
why can it not be a term of y, only x?
which one?
This method, when you write method, means this gx.
See, I have
So,
started with, see, wait a minute, I just want to clarify you. See, whether you are confident that, so see, here left hand side is a function of x only. Okay,
yes,
because
sir.
we have started with the case that let mu be a function of x only. So mu is a function of x, so d mu b by dx also a function of x, right?
Yes, sir. Yes.
Okay, so when the left hand side is a function of x only, so right hand side could not involve the y itself. That's the identity. Okay, so
Sir, if the right side is a y, then it can be also some equation that
it
if
is
the
not.
left,
See, this equality is not possible if you have the right side as involving y.
so sir, if we have a function like x square minus y square plus 1 is equal to 0 or anyone,
Pardon?
so the left side is x square and right side can be a y square plus 1. So what is the
No, I didn't get you. What your point?
uh,
Yeah,
uh,
you just give me give me example again.
x square plus y square minus 1 is equal to 0? We can write that, means equation.
Huh?
So if we compare that with this one, so left side is only a x term, so we can
Wait. I just writing. You have given x square plus y square minus 1 equals to 0.
yes, we can
Okay. Now
yes, sir.
see, I just write x square is equals to 1 minus y square.
Yes, sir.
Okay. So this is your point, right?
Yes,
So you
so
are
sir,
saying
I
that, see, sir, this is this side y is involved, this side is x is involved. See, I'm
yes, sir.
telling you, x is a function, x is a independent random, sorry, not random. So x is a independent variable. Okay, but y is a dependent variable on x. So it's again, so this left hand side is a function of x only. Right hand side is also some function of x only. It's a function of x only. It's ultimately getting down to function of x only. Did you get my point? Y is it depending on x only? Whenever x is changing, this y value is also changed, right?
Okay, yes, sir. Okay, sir. Yes, I got it. Okay,
Okay.
okay, sir. Yes, sir. Yes,
Yeah.
I got.
Okay. Now, let's consider the case 2. So this is a one method. So case 2 is let mu of x, y be a function of y only. That also possible, function of y only. That also we cannot get rid of this case as well. So in that case, what will happen? This implies that dou mu by dou x is 0. Okay, and then double star, what it will gives you is you have the following. Uh, so dou mu by dou x is 0. So you have this m time base is equals to this. Okay. So you have this is equals to m time dou mu by dou y is equals to mu time dou n by dou x minus dou m by dou. So since mu is a function of y only, so do again with the same all this like all words you can say, okay, what we have mentioned earlier as well. So we are following up the same thing. So this is d mu by dy 1 by mu is equals to dou n by dou x minus dou m by dou y divide by m, and which is purely is a function of y only, so that we can denote it by, let's say, h of y in this case. And you can certainly write this implies integrating factor. I'm straightforward writing that is equals to mu, that is equals to e to the power integration of h of y dy. And what is h of y is? H of y is equals to, this is dou n by dou x minus dou m by dou y divided by m. So this gives you the method 2. Okay. So I can see this is here method 2. So method 2 is for, means these methods are to identify the integrating factors. Okay. So if you have dou n by dou x minus dou m by dou y divided by m is a function of y only, say h of y, then integrating factor is equals to mu, that is equals to e to the power integration of h of y dy. And you can certainly verify afterwards that mu, if you multiply the original equation, that resulting equation is going to be an exact differential equation. Okay, so I will complete this with y. H of y is equals to dou n by dou x minus dou n by dou y divided by n. Certainly you will get this by solving the examples, but here what is how do you verify whether this method works, or if method 1 works or method 2 works? Okay, see, in any case, to verify that whether exact or not exact, you have to certainly find out dou m by dou y and dou n by dou x. Okay, so then take the difference of them. Okay, so certainly if they are equal, exact, you know the how to solve it. If they are not equal, then take the difference. So here also see dou n by dou x minus dou m by dou y. You previously you have seen dou m by dou y minus dou m by dou x. Take the difference and factorize it. Okay, so take the difference and factorize it. Okay, and then you see whether that factorization, after factorization, whether it contains the factor from m or factor from n. After removing those factors, suppose after means like it contains the factor of m. So if you divide, if suppose you remove that factors from m, whether it is remaining as a function of y only or not. Similarly, if that resulting here difference, if after factorization contains the factors of n, and if you remove those factors, whether remaining is a function of x only, it falls into the method 1. Okay, so this is how you can means like you can judge from the first time, is like first equation on means I can say first result onwards, that dou n by dou x equals to dou m by dou y or not. That you can from there itself you can observe that whether it fall into method 1 or method 2 or no, none of these methods. So these are both are the same simple cases. Okay, similar cases you can say. Okay, so there may be a chance that that integrating factor may not be a function of x only or y only. It may be function of both. Okay, so method 3 I can give you here is so what you can do is method 3, what you can try is, okay, see, one method is intuition method. Okay, that's a that's I'm just it's like I'm not mentioning here. Intuition method means you have to guess. Okay, but that guess means you may or may not be able to guess always. Okay, so that method I'm just getting rid of this by looking at the equation, whether you are able to get any function of x and y, after which multiplying your resulting equation becomes exact. If it is a non-exact, started. Okay. Okay, so two methods you're already aware now. Another method is, let's say, if, so I'm mentioning here, so if this m dx plus n dy be such that is equals to 0, is non-exact. So if it is exact, we are not worried about. Okay, non-exact differential equation, and is such that you have this is y into some function of f1, let's say x into y dx, plus x into some function of x into y dy equals to 0. Okay, there are two cases. So there are things if such that, then integrating factor is equals to 1 upon mx minus ny, provided mx minus ny should be non-zero. So this must be defined. Okay, mx minus ny must not be 0. If it is not 0, if it is 0, 1 by 0 is infinity, so that's not it. Yeah. So now I hope you can you can understand from there that dx coefficient you can take y out, and dy coefficient from there x out, and remaining whatever the in the factor of this remaining is a function of x into y. Okay, or you can say you can replace x into y with some d, where d is equals to x into y. So for example, I'm give you one example here. Simple example is, let's say, y into 1 plus 2xy dx plus x into, okay, let's say sine of x into y plus 1 dy is equals to 0. Okay, so this you can recall now. Just see m dx and dy. Now you have to see whether, see, this is not exact differential equation. Why? I can say straightforward is because this n involves the sine function and m does not involve any sine or cosine function. So whenever you are differentiating with respect to x or with respect to y, differentiation is cos will certainly take place, but which is not happening in m. So I can certainly look from here itself that it's not going to be an exact differential equation. But what I can feel here is, see, into, so dx coefficient has y factor, dy coefficient has y x factor. If it is not, if it is maybe inside y plus 2xy square x times sine xy plus x, so that you can take out. What is remaining inside is nothing but a function of x into y. See, constant term can be treated as any function because this can be written as x into y to the power 0. Okay, so second term you can look at here, second term function of x into y. See, how would you verify that it's a function of x into y or not? To replace x into y by d. Let me replace x into y. So let me, I hope I already got it. Maybe. So see, let d equals to x into y. Okay. So this implies m is equals to y into 1 plus 2d, and n is equals to x into sine d plus 2. So what is this? This is equal to y into function of d, and this is n is equals to x into some function of d. So this is how you can this is a function of d. So this is now fall into this case. Now what I can give you is here, you can verify now. Yeah, exercise now. So mu is equals to 1 upon mx minus ny. Okay, 1 upon mx minus ny. I'm talking about this case. Verify the following. So verify dou by dou x, dou by dou y of m time mu is equals to dou by dou x n time mu. That you must verify. Okay, and that will tell you that resulting equation after multiplying by this will become an exact differential equation. Okay, right. So this is a one of the technique here. Another technique what I want to mention here, method 4. So you have this method 4. Is let m and n be homogeneous of same degree. Okay, and m dx plus m dy equals to 0 is non-exact differential equation. Okay, then I'm giving you integrating factor is equals to u of x comma y, that is equals to 1 upon mx plus ny, provided mx plus ny is not 0. See, these things you can still work out, or you are able to, if you get a time, you can work out this problem by referring this result. Okay, where we have derived the double star. So you derive the double star and try to use some. Okay, so there is a result. Okay, Euler's theorem for homogeneous function of degree 1 or degree 2 or degree 3 or degree n. Okay, so that you try to use if you want to verify that derivation, whether that is correct or not, or else what bring some of the examples here which you have is like in tutorial sheet. You have some of the problem which are falling into this category, is like m and n be homogeneous function of same degree. So what does that mean? I'm just writing here. So then in that case you have, this is let's say then dy by dx is equals to minus m by n is an homogeneous equation. Okay, that is the meaning, homogeneous differential equation. Okay, so if you rewrite all the things, you will write dy by dx equals, so this in the right hand side becomes a homogeneous function of degree 0, because m is of homogeneous of same degree and m and n both are of homogeneous function of same degree, so degree will get cancelled. If you replace x by lambda x and y by lambda y, so lambda is going to cancel, it will remain with the same here. Okay, so there you have used the transformation. Okay, there you have used the transformation. Now here you have another method. So you try to attempt both the things here. Okay, for some of the one or two problem at least. Okay, and try to verify that whether this becomes an integrating factor or not for that particular problem. If it is not exact, if it is exact, you can straightforward solve this. Okay, right. So there are 4 types now, and one other type is intuition method. So that is a separate thing. Okay, so let's see some of the problems. Okay, so I'm just skipping these things. Okay, not giving you, yes. Okay, Now, determine whether or not each of the given differential equation is exact. Solve those that are exact. So I'm just going to check the condition, okay, that whether this becomes exact or not, or we try to identify which method it will fall into. Okay, so the very first thing, for this case, dou m by dou y, I'm straightforward. M is the coefficient of dx. So I'm particularly concentrating here. What is dou m by dou y is 4x. Dou n by dou x is equals to 4x. So this is an exact differential equation. So I don't need to work anything here. Okay, right. Now for the second case, what is dou m by dou y is the coefficient. We are differentiating partially with respect to y, the dx coefficient. So that is going to be minus 2x sine y plus 3x square. And what is dou n by dou x is equals to 3x square minus 2x sine y. So both are equal. So it's again an exact differential equation. We don't need to find out the integrating factor. Now for this case, so dou m by dou y is equals to 3 plus 8xy. And what is dou n by dou x is equals to 2 plus 6xy. Now both are not equal. So this is not exact differential equation. Okay. Now let's try with this very first thing. It's not falling into the homogeneous case. Okay. Y into. So sorry. 3y is a term of degree 1. Second term is of degree 3. So m is not of homogeneous function. So there is no need to check for m. Okay. Now what you can see is now here and I am having here m is equals to 3y plus 4xy square. I can certainly take y out from here, and what is remaining is 3 plus 4xy. And what is n is 2x plus 3x square y. And I can certainly take x out, and what is remaining is 2 plus 3xy. Now, you can, if you carefully look at it, this is y into function of x into y. And this is x into function of x into y. So surely it falls into the method 3. Okay, where we have seen. Okay, and we have one of the integrating factor is 1 upon mx minus ny. Okay, now, so what is from here, mx minus ny is equals to multiply by x. So you have 3xy plus 4x square y square minus 2xy minus 3x square y square. So that's going to be x into y plus x square into y square. So that is equals to x into y times 1 plus x into y. So this implies integrate, so which is certainly non-zero. Okay, non-zero means, okay, non-zero means what? You can consider a domain where it remains non-zero. Whenever x and y are non-zero, you can consider that domain. Okay, where it will never vanish. So integrating factor is equals to 1 upon mx minus ny. That you can simply verify. Okay, and then this is your mu. Okay, and then you can solve the resulting equation new. Okay, new equation as you have done for the previous case. Now, what I am doing here, I am again checking what is the dou m by dou y minus dou n by dou x. So what is this? So I just want to check. So dou m by dou y minus dou n by dou x is equals to, so 3 minus 2 is 1, 8 minus 6 is 2. Okay. So is 1 plus 2 into xy. Now look at here. So what is m? So do we have any factorized form here? going to be 3 plus 8xy, 2 plus 6xy. Okay. Okay, so there we are not getting anything. Okay, so now what is m is have m here, x into this 2 plus 3xy. What is m is simplified factorization form. Now you can see that this is does not have, this does not contain any of the factors, so that type is gone. Okay, so means this means if you whether you whether you are going to divide both sides by n or n, it never be coming out as a function of x only or y only. So those type has gone. Now what I am interested here is I just want to reframe it. Okay, and what I can do is okay. So what I can do is I can modify this equation. I'm just going to, let's say, equation number 4. I have, this is 3y square. So I'm just going to 3y plus, let's say, 6xy square dx plus, the thing is, I think fine, 2x plus 3x square y, 2x plus 3x square y dy equals to 0. Now, we certainly fall into the previous category. There is no other doubt about it now. Okay, y into function of x into y, x into function of x into y. So I have changed this 4 into 6. Okay, now what is, wait a minute. So let me see whether what is dou m by dou y is going to be 3 plus 12xy. Okay, and what is dou n by dou x is equals to 2 plus 6xy. Okay, so what I can do here is I can make it as 5x square. I am just trying to get it something. Okay, I just want to show you something. So 2 plus, let's say, 10xy. Now what is dou m by dou y minus dou m by dou x is equals to 1 plus 2xy. Okay, now see, this certainly fall into that method 3. So we do have advanced integrating factor. Okay, now what will happen here is, now what is m is y into, or 3y into plus 2xy, and capital N is equals to x into 2 plus 5xy. Okay, now you can see this 1 plus 2xy is sitting as a factor of m as well. And after removing that factor, dividing by m, its remaining is a function of y only, because only 1 by 3y will be there. Okay, so now, so certainly this implies dou n by dou x, or dou m dou y minus dou n by dou x divided by m is equals to 1 plus 2xy divided by 3y times 1 plus 2xy. So this will get cancelled, 1 upon 3y, which is a function of y only. So this also falls into the second case, function of y only. Okay, so there are two integrating factor you have, means from here I'm telling you that whenever you have an integrating factor, it is not unique. Okay, so you may have different integrating factors, somebody else also have some different integrating factor. Okay, and what is the nice thing about if it falls into it here, so then, so now see, in the method 3, what you are having is dou n by dou x minus dou m by dou y. You have to keep track that as well. So it's a negative of that. So now, so this implies, so in original method, so dou n by dou x minus dou m by dou y divide by m, that is equals to minus 1 upon 3y, and that is equals to your h of y. And integrating factor what will be the integrating factor is e to the power integration of minus 1 by 3y dy, and that is equals to nothing but y to the power minus 1 by 3. Okay, so this is the see, simple integrating factor. Rather, if you are doing with let's say 1 by mx minus ny, so if you try to identify what is 1 by mx minus ny is going to be, so this is one of the integrating factor. Another integrating factor is second integrating factor, you can say, is equals to 1 upon mx minus ny, so that is equals to 1 upon mx, so is 3y plus 6xy is 3xy plus 6x square y square minus ny. So n is 2x, right? 2x square plus 5x square y square. So 2x y plus 5x square y square. So that's with minus sign. 1 upon. So that's going to be 1 upon. So 3xy minus 2xy is x into y plus x square y square. So this is going to be 1 upon x into y times 1 plus x into. So this is another integrating factor, which is a rather complicated integrating factor. Why? Because when you are going to adopt this integrating factor, then it will be difficult for you to integrate the perform the integration. You have to use so many other results, standard results there. So you can try with both the integrating factors. Okay, for this case, it is very it will be rather simple than this case. So you have two integrating factor. One of them is simple. Okay, right. So I think we can add here now.